Can you hear me if I don't sort of lean towards the mic? Is it good? All right. I think it's about time to start. Thank you everybody for coming. Thanks to those that are staying. Thanks to those that are coming from different rooms. Appreciate it. The competition is fierce, so really appreciate it. My name is Adam Welc. I work for Uber engineering, and I'll talk to you today about some of the efforts around automation that my team and my extended team at Uber has recently undertaken. So, clicker works. First, a little bit about myself. I work what's called a programming systems team at Uber. It's a very small team, about 6 or 7 people. We're like a little kernel of sort of programming languages and systems research and engineering, much like Facebook or Google have, but we are 6 people that have hundreds, so that's the main difference. We're part of the larger organization which is called Developer Platform, and both my team and the extended Developer Platform team have several goals, reasons for our existence, if you will. One of them is to improve developer experience, obviously, and make their lives easier, their work more efficient, but also we work on, this is really squeaky, but also to work on improving performance and reliability of our application and service. So the distinction is mostly that Uber has, as you might have noticed or used, the mobile apps, which are used by drivers, but also obviously by people that use the service. And services are everything that runs in the backend and supports those applications in the backend. In this talk, I will focus mostly on the developer experience, since automation is kind of more on that side of things. First of all, let's define what we mean by automation. It can mean many things. I don't know, robots, for example. Since I work at Uber, you may even think evil robots, but that's not what we're talking about here. This is more about basically reducing manual effort. So whatever the programmers, the developers have to do, if we can make their lives easier through automation, that's what we're trying to do. And it doesn't necessarily mean, the title of my talk hopefully was understood to be a little bit tongue-in-cheek. We didn't automate everything yet. We didn't fire all the developers. We have a fairly strong engineering team. It's just, again, to make their lives easier and their work more comfortable. So I will talk today about a few selected projects. There is a lot more going on, both on my team and on the extended team. The projects I will talk to you about today, there are 3 of them. One of them, the first one, is basically our build system, or part of our build system. It's called SubmitQueue. It's how to make it scalable and convenient for developers to use. And I'll talk more about it a little bit later, what this really means. Then I'll talk about an automated or automatic code cleanup tool. It's basically that code elimination, but with a special sort of twist. That's going to be the second part of the talk, and the third part of the talk is actually going to be about our efforts to deploy an existing tool to do certain optimization for us, and also sort of make this into an infrastructure that's basically automated. So let's start with the SubmitQueue. This work has been done on my extended team, the developer platform team, and there was a paper at Eurosys last year published based on this work. If you're interested in more details than I'm going to cover today, certainly you can read the paper. There's also a blog post at our engineering blog about this. All right, so let's start with something that Simon Marlowe has mentioned in the morning already, which is the infrastructure that our developers use to build their software. There are 2 alternatives, and one of them is basically every team has their own repository, and they somehow very painfully manage dependency between those repositories themselves. Or there is one larger repository. There's not necessarily one huge repository for the entire company, but at least per, say, language or per large organization. And we call those monorepos. And Simon mentioned that Facebook and other companies like Google and Twitter, they also use monorepos. And there has been many discussions on why monorepo architecture is actually useful and why it's convenient for developers. There has been a paper at ICSI also last year that talks about some of these things, but basically it's about dependency management. You don't have to worry about different teams using different versions of different libraries and trying to reconcile this across the entire code base. And also, it's just easier to analyze things because you have everything in one place. You don't have to like worry that somebody changed something you didn't know, and your tool that I don't know, checking nullness that used to run properly is not running anymore because somebody changed some code in one of the repositories. The side effect, though, is that there's a lot of developers working on the same repository, right? So there's a lot of people that are committing changes into the same code base at the same time. And now, in our case, we have overall over 4,000 engineers with, I don't know, at least 300 or 400 working on our mobile apps, and probably as much or twice as much even working on our services. So you can imagine that if a Monorepo holds code for all our mobile apps, you have like 300 developers committing to that repository over and over again. It's literally 1,000 commits a day sometimes. So what's the problem? The problem is that if you had, in this case, you have only 2 developers, Alice and Bob, but you can imagine there is way more of them. So the problem is that even if you have a repository that's in what's called a green state, which means that everything runs, right? Everything is correct, all tests pass, everything is great. So they can ingest source code from that repository to their local workspace, and obviously everything is still good, right? So they make their own changes, they make their own local compilation, everything works great, they run some local tests, everything works great. However, not everything has to work great once they start pushing changes to the common repository, because the changes can conflict with each other without them knowing this before they actually push the code to the Monorepo. And you may ask, what kind of changes are what those would be, or what the example of that. And that's one of those. So you don't have to read the whole code. Let's see if the thingy just works. Okay. So this is just one example, and it's actually a real example of something that happened in our Monorepo. You have 2 people. This is one patch from one person. It's another patch from the other person. Both those patches were correct according to local testing. But when they pushed it to the Monorepo, there was a conflict. And why was there a conflict? Because they both, in different parts of the code, used the same name for a local variable. And that basically caused a conflict that was undetectable before they pushed the changes to the Monorepo. So another question that you may ask is, how often does that happen? Like, is this really a problem? So that chart is based on historical data from, I think, a couple months that have been analyzed by our developers. So what's on the chart? What's this thing? Okay. On the y-axis, you have a chance of conflict. So basically, what's the probability that the conflict will happen? On the x-axis, you have how many concurrent changes have been sort of created and pushed at the same time. And the line shows you basically how the probability grows. Yes, Sophia?
What does potentially conflicting mean?
It just means that it hasn't been proven that they're independent. So they basically are commits to this.
Everything that is concurrent potentially conflicting?
That's a tricky question, and I will talk a little bit more about that. It has been like that in the past when that measurement was taken. It's not like that anymore with the new system that I'm talking about after that system has been deployed. It's basically like you can tell based on the build targets and historical data whether things are conflicting or not, with probability or with certainty, depending on what you look at. But at that time, I think that that basically means that all changes potentially were conflicting with all other changes. So the bottom line from this figure is that the more changes you have, the more the probability grows. So even with like 12, this is just a 1 point, right? But with the 12 concurrent changes, you get about 20% of a conflict, chance of a conflict. The more I actually don't know if we did a measurement beyond the 16 concurrent changes, but that's at around 45% chance. So it's a pretty high chance, and it actually does happen a lot. So we know the conflicts are bad, and I think based on the chart that we just have seen, which shows that the conflicts happen pretty often, we can agree that having a red master is bad, meaning that basically that these types of conflicts will happen often. And this slide just emphasizes the reasons why developers and managers and VPs don't like that to happen. So the first reason is delayed production rollouts. That obviously translates to money. So imagine that you have a release, a weekly, bi-weekly, monthly release, and on the day of the release, some developers commit code that makes the master red. That obviously means that you cannot release. God knows how long it's going to take to roll it back, because rollbacks are actually complicated in this scenario, because you cannot roll back to an arbitrary version. You have to pick a version that you know was green. You don't always know which of the last versions was green, because you don't always track these types of things. And of course, for developers, it's not great either, because you can ingest changes with the problems that manifest themselves in the monorepo. So basically, you break the master, and a bunch of developers ingest that broken master and start working on it. Right? And only after they start running local tests, maybe they'll discover that the master is broken. They will not know if the master is broken, or if their local version is broken because of the broken master, or their own local change is breaking things. So it's all a big mess. So what's the challenge? The challenge is to basically eliminate all this manual effort that's related to having, at least on occasion, a red master. Basically trying to get rid of that effort and trying to do it automatically. So that's what we call an always green master, and that's kind of what the system I'm talking about is delivering to our developers. So there are a couple ways to accomplish this, and some of them are still being tried in the industry or are in place in industry. The first one is like the simplest one. Basically, don't push anything concurrently, right? So serialize every change and don't push another one to the master before the previous one is considered successful, the previous push is considered successful. That doesn't really scale. So even if you can, like an average build time in at least for our Android mobile app is, with all the tests, UI tests, integration tests, everything, it's about 30 minutes, maybe a little bit less, but let's assume 30 minutes. So if you have 1,000 of those, then you would wait 20 days for a turnaround from the last submitted change to actually end up on the master. So that's really not what we want. This really doesn't scale. So the next obvious solution, or the next obvious optimization of this, is batching, right? So instead of submitting one change at a time, waiting for this change to be successfully merged and tested, you do it in batches. And that may speed things up. There are systems that actually try that. I think one of the Google projects, Chromium, I think, maybe, infrastructure has this system in place. The problem, again, is that there is a lot of manual effort that is required when the batches fail. And the more updates you have, the larger the batches are, and the more often they break, and the more often you have to have like build masters or whatever they're called in your given org to basically manually figure out which of the updates in a given batch have failed and roll them back. It's all, again, it's becoming a mess with excuse me, with a large number of changes. And the next solution is optimistic speculation. And I think there's, and again, there are systems that try to do that. One of them is called Zool. So what they do is basically they allow concurrent changes, but for each change, it's assumed that all the previous changes will be merged successfully. And this would work, again, with low contention and a small number of developers, but with the conflict rates that are raising with the number of concurrent changes, the optimistic speculation we felt more and more often. And again, it's not only doesn't scale very well, but it's also very unpredictable. So basically, you don't know whether or what's the probability of your change actually landing successfully. So that's what our system, which is called SubmitQueue, is trying to solve. That's the problem we're trying to solve. This is sort of the overview of how this works. So we have a distributed SubmitQueue, which is a bit of an overloaded term here, but basically this is a queue that accepts changes from users simultaneously. And we have a speculation engine, so it basically takes those changes that are submitted to the system, or we call them pending, and it tries to figure out what are the builds that it can try that will have the highest chance of succeeding. And what that means and how to calculate this is sort of the gist of this part of the talk, and I'll talk about it later. There is also a conflict engine, or conflict analyzer, which tries to figure out what Sophia asked for a couple minutes ago, which is it tries to figure out which of the changes have a chance to conflict with one another, and those, of course, are going to be better ones to try, and this information is being fed to the analyzer so that it can make a more educated decision. Finally, there is what we call a planner engine, and it basically takes periodically the information from the speculation engine, selects the best builds that the analyzer engine, that the speculation engine has found, and tries to execute them, see which succeed, see which would have to be aborted, and those that succeed obviously are at some point pushed to the monorepo. So that's sort of the general overview of the architecture. Today I will, since I have 3 projects to cover, I will mostly focus on the speculation engine. So what does it do? How does it do what it does? So how does it actually select builds that are most likely to succeed? So in order to do that, it builds what we call a speculation tree. So let's assume that we have, in the queue we have 3 pending changes, C1, C2, and C3. And we'll be building the speculation tree, which represents builds, right? And build is what we call the steps that are needed to commit a given change. So B1 are build steps that are required to merge C1 with the current head of the monorepo. Okay? So the next step is, obviously, there's more than one change. So there's not much we can do with the change or the build for change number 1. But for build number 2, for change number 2, there are sort of 2 things we can do. So we can kind of assume different realities, right? And we can pre-compute results based on what we think is most likely to happen. So in this case, we basically assume that the build 1 fails. So B2 has to be merged with and tested with the head of the monorepo separately. This, on the other hand, assumes that B1 succeeds. So basically, you can batch together the changes for B1 and B2 and test that build and see what happens as a result of that build. So basically, what this means is that change C2 will be it can be committed based on either result of this build or that build. Okay, and this just keeps going, right? So you sort of build those, or at this point you don't build anything, but you build the tree, right? So you have these different changes, and you have different results, and you pre-compute results on different realities. So what you could do, technically, if you had enough resources, you could try all those builds, right? So you could try B2, B1, 2, B3, B2, 3, B1, 3, B1, 2, 3, and basically those that will succeed or those that will fail will lead to computing the further part, the bottom part of the tree. So essentially, if you had B1 running and B1 failing, then you would start evaluating this part of the tree. This one would no longer be valid, right? But this is still impractical. There's still too many builds that you're going to try. They're going to fail. So ideally, we would like to pick the builds that are most likely to be needed to commit a given set of changes that we have in the queue that we have pending. And that's what the speculation tree is used. And how it is used, I'm going to show you in the next couple slides. So this is basically the same tree, and a little bit of new terminology. So we're basically looking for values for each of these builds that basically determine the probability that this build is going to be needed to merge a given change that represented by C with the monorepo. So the first one is B1, and this is the beginning of the the evaluation. This is the first change that has been put into the queue. So basically, B1 always decides if that change is committed or aborted. There's no other builds that can decide that, and therefore the probability is 1. When we move a step further, you will see that when build B1 succeeds, that basically the edges in this graph or in this tree show the probabilities that which part of the tree will be evaluating next. But they also determine the probability of the builds that are in the lower part of the trees to succeed. So in this case, if the probability that B1 2 will be needed to evaluate these builds is equal to the success probability of build 1. And on the other side, it's obviously the reverse of that. So actually, the math here is less important, and you can find the details in the paper. The main sort of conclusion or the main observation from that set of slides is that because you can keep going with these computations down the tree, is that you can determine most valuable builds based on the success of merging an individual change, and based on the probability of two changes conflicting, right? So, even in these more complicated changes, this is all you have on the right-hand side, and this is basically the only thing I would like you to remember from that slide. So what this really means is that if we know or if we can estimate these values pretty well, then we can fairly well decide or fairly accurately decide which builds are going to be those that will be succeeding, those that are going to be most needed. And there is a little bit of machine learning in this. So I'm slightly competing with the ML talk from Facebook next door. So what we did is we built basically a logistic regression model that estimates probabilities of those builds to succeed. And we took months of existing data and we ran it through the regression engine. There are some features that were selected to be sort of the most important based on experiments, and we'll talk about them in a little bit. But basically, we achieved the prediction accuracy for those probabilities on the order of like 97%. And the features that were deemed to be the sort of the most important, the most relevant to selecting the builds were actually basically in 3 categories. So the first one is developer. So it appears that it's important to know which developer works on a given change or a given set of changes, because some of them are more experienced, some of them are less experienced. Some of them are more comfortable with one programming language, some of them are more comfortable with the other programming language. So there was actually a very sort of the predicting factor that worked really well. So name, just because you have to identify them somehow. The change itself, or the sets of changes themselves, were obviously very important. So one of some of the criteria that were related to the change was the number of commits. So a change doesn't necessarily contain only one commit. You may basically refine your change multiple times. And we found that those changes that had more than one commit, that were refined over and over again, they tend to succeed more often, for example, right? So that was also a very good predicting factor. The number of files changed, the number of affected build targets, all of these were important for predicting value of whether a given change separately can succeed. Whether the 2 changes conflict with each other, there were slightly different set of features that were important. Some of them are listed here. So if you had 2 changes with a large number of common targets, build targets, that would indicate that they will conflict more often. Same with like the number of files that were common between 2 different sets of changes. Those would also conflict more often. There were other features. Again, we had over 100. Those are just selected because those were the sort of the most valuable one for prediction. So results. The way we run the evaluation, the performance evaluation here, is that we use real changes. Obviously, different set of changes that we use for training. But we also implement an oracle. So basically, an oracle is a system where the prediction is always accurate. So it's always correct. So the oracle always knows whether 2 changes conflict and what's the chance of a given build to succeed. So all these numbers are normalized with respect to the oracle, and this shows the 50th percentile. Basically, the main number here is that under sort of low contention, we're basically as good as oracle. So this is the number here, and this is sort of the worst case scenario. Same setup, but it's the 99th percentile, and this is the sort of worst case scenario. So we are about 4 times as slow. But this is the contention where that's typically not operated. Like we don't typically operate our build system at that contention. Overall, it's been working really well for us. But this just shows sort of the average low contention case and the sort of the worst case scenario, so that we can't claim that it works perfectly in each case. So that's sort of the end of the first part of the talk. How am I doing on time? 20 minutes to go. It should be totally fine. So the next project that I'm going to talk about, the next effort around automation that we are working on, we call it Piranha. It's actually an open source project. So if some of you that are working in the industry are interested in having similar tool working on your code base, please come talk to me after the presentation, and hopefully we can make it happen. So what's the motivation here? The motivation here is that that's basically the experiment setup that we have at Uber, and it's actually it's not unlike experimental setups for experiments in other big companies. Basically, our developers love experiments, and they run hundreds of them at the same time, live in production, in basically your apps and the driver apps. So the way it works is that you have a flag that is supplied by the server to your device, and on the device, basically the code determines a control flow path based on the value of that flag that tells the application to either to run some version of experiment or to run a control version of the experiment. So that's how it works. And the problem is that these are experiments. So they typically last for only a period of time, and then they either become features, non-experimental features, or they become defunct and they are no longer tried ever again. The problem is that developers are not always diligent enough to clean up after themselves, and a lot of code that's due to or related to the experiments that have been run in the past is still out there. And that is a problem for large code bases, especially code bases that are stored in the Monorepo, where everybody's looking basically at the same code. When you have this kind of litter, it affects readability and the maintainability of the code, because you have code that's basically dead, but nobody knows, right? So they look at the code, they don't know if they should test for it, they don't know if their code should interact with that code somehow or not. And it also blocks the binary, because not all of this dead code can be removed by the binary sort of level dead code elimination tools like ProGuard or Redux. So this is an example of how this looks sort of in semi-real life, because that's obviously pseudocode. But basically, that's literally how this works or how this looks in our code base. You have some class in some file, it's not necessarily one file, where you have an enumeration that determines the names of experiments. And then you have an actual sort of application level or sort of some code that executes the application logic that is trying that experiment. And it has a conditional that uses an API of some kind from our sort of testing suite to see if it should run experiment or it should run a control group for that experiment. So what can you do about it, right? How can we how do we actually clean that? What can we do to automatically clean that code? So imagine that hypothetically, that we know that this conditional will always return some value, let's say false, right? If we knew that, somehow, magically we knew that, then all of this code would be redundant, right? I mean, we could remove it. If that conditional always returns false, the code that this conditional surrounds is never executed. If it's never executed, then we don't even need the definition of the experiment and the enumeration, right? So if you only knew that. So that's what Piranha does. Piranha is an automated system that basically tries to figure out these kinds of cases and generate patches, reviewable patches for developers that remove the code automatically. So the input to Piranha is a value of a flag, assuming that the flag always returns the same value. So the server always supplies the same value for a given flag. There's also a timing component, so it has to be doing this for a certain number of days, right? If it returns the same value for the flag for 5 seconds, that doesn't really mean that the flag is stale. But if it returns the same value for the flag for 5 days, that probably indicates that that flag is stale. And again, automatically generated reviewable patch is the result of Piranha. It's the output of Piranha. So how does it how is it implemented under the hood? We have basically an AST traverser, if you will. For different language. For Java, for Android, we use Aeroprone, which is like a Java C plugin. That's the tool created at Google. And for iOS, for Swift, we use Swift syntax, which is basically the same thing. It allows you to traverse and modify ASTs. So what happens during the traversal? You traverse the AST, you identify places where the API calls to our testing framework are being made. You get the value that you got for a stale flag, and you basically partially evaluate. Right? So you evaluate the conditional, you know what the semantics of the API call is, and you determine if the code that the conditional guards can be removed, or maybe the conditional itself is removed because the value is always true, right, in the previous example. The tool rewrites the code. We transforms it back into source code, generates a patch, sends the patch to the reviewer, original reviewer, and to their manager, and sometimes to their manager's manager. But you get the idea. And periodically reminds the developer that the patch is there. Please take a look at it. There's something to clean up. So that's basically how it works. So if you put it all together, there are a couple components of the system. This is our orchestration engine for tests, which contains all this information about the flags, and they can be queried by basically a CI job, the continuous integration infrastructure job, that gets this information from the test orchestrator. So which flags are stale? So that's the information that flows. The green basically indicates flow of data, so to speak. So it gets the information about the stale flags, traverses the ASTs. That CI job basically does everything that's Piranha, right? So it traverses the AST, generates the patch, sends it to the developer. The developer hopefully doesn't have to do much with that patch, maybe some cosmetic changes, and can push it to the submit queue to be merged with the tip of the monorepo. And there is the Piranha tidy, which periodically pings the developer and their superiors to make sure that something happens with that patch, that it gets reviewed and hopefully pushed and merged. So we have about 30% of the patches that are generated by Piranha. That's like the number so far. And that system has been around for about a year or so. We have about 30% patches that are basically don't require any additional intervention from the programmer. So they see the patch, they look at it, they press push button, and then it goes to the monorepo. These are some additional results and some limitations of the tool. It's not a perfect tool by any means. There is more work, and we are working on extending it. The numbers are basically as of a week ago. So we have about 280 flags, stale flags removed on Android, and about a little bit over 500 on iOS. So these are the numbers. In terms of the code itself that has been removed, the patches are between 10 and 100 or hundreds lines of code. They're not huge, but ultimately, I mean, it's for code comprehension clarity. So it's an important piece. We're working on what's called Piranha Dip Clean. Some of the limitations that the tool currently has are related to things like, what if the API calls from the testing framework are wrapped around other calls? Like, we don't really know at this point that we know how to handle this, but the tool doesn't handle it at this point. There is also an issue of some tests that may rely on the code that the Piranha has already removed. At this point, there is no sort of correlation being made between these pieces of code. That's, again, the next step. And finally, if the code that gets removed is called from a private method, actually calls a private method, and only this code calls the private method, then that private method can also be removed. We don't do anything about methods that are not private, even though sometimes through whole code, whole program analysis, you could probably remove those as well. So there's going to be some work in that direction as well. And that's it about Piranha. This work has been done on my team, the main person on this project, and thanks to him for providing the details and helping with the slides a little. It's Murali Krishna Ramanathan. If anybody wants to get like the deepest details about this project, then he's probably the best person to talk to. So the last bit of automation that I wanted to talk to you about today is related to not actually building a new tool, but rather taking a tool that already exists and trying to deploy it in, well, in our setting, but generally in production setting. Oh, so the tool is Redex. It's a tool from Facebook. They've been using it for quite a while now. We only started about maybe a bit more than 6 months ago. But the first sort of successful deployment that we had was about 6 months ago. So what's the motivation for this work? The motivation here is that our apps are, maybe you noticed, maybe you didn't, but they're getting more and more complicated. There are more features. There are things like, I don't know, London, I think, has recently started seeing our red electric bikes, jump bikes. So those have been integrated into Uber app at some point. There are some cities in the US, I think, I'm not sure about outside the US, see the public transport integration. So you can basically buy tickets for metro, and when you get out of metro, you can take Uber. And so all of these new features make the apps not only more complicated, but also larger, and also lead to like more data being sort of processed and more classes, in the case of Android, being used. And as such, startup time also suffers. So we've seen basically a negative trend of the startup time for both the rider and the driver app for quite a while. So the idea was, or the challenge was, what can we do to mitigate that trend? What can we do to at least sort of level it up, maybe start getting it a little bit lower than it used to be. Again, the idea was we don't have the resources yet to build super complicated tools ourselves. So why don't we, or at least not all of them, so why don't we try and look around and see if there is something there that could help us? And yet there is. Yes, there is. The tool from Facebook looked like a great candidate. Again, they've been using it for a while, many years. So it should be simple, right? You should be able to download it, run it by hand, maybe right before the release, and everything should work. So it should be really simple. It should be really great, low sort of effort, low resource kind of project that should give us a lot of bang for the buck. Not so fast. That ended up being automating this and getting it to work was actually quite challenging. And so this is like basically a bit of a war story on what it took to get this to work. So the first challenge was, like, how do we even start? I mean, what I described in one sentence sounds simple, but even when you start thinking about deploying anything, like really literally anything, any tool, be there from industry or from the academia, in the setting of a fairly large corporation or fairly large engineering organization, it ends up being difficult. So first of all, like, we are kind of researchy team, a little bit at least, so we're not working on actually releasing the apps ourselves. That's what the release engineers are for, and they're really, really nervous people. Like, if you want to change anything in the build pipeline, or you want to do some kind of code transformation or anything, they're like, oh no, this is going to crash, and we're going to lose money. And they're actually rightfully paranoid, because that does translate to actual losses in monetary losses if our apps crash, both on rider and driver side. So you have to do a lot of stuff before you even try a beta. Like, it's not, you can just turn it on and hope for the best. Maybe like, when Uber was super young, like, 1-2 years old, that's what people were doing, but not so much anymore. So we had to do a lot of testing, both different OS versions, different devices, to basically even like try to convince them that we should try that. And also, like, this tool is really a bytecode to bytecode optimizer that implements a ton of optimizations. You can choose a ton of passes and you know, with varying degree of sort of potential success and potential gain. So we had to be really careful what to choose in terms of both the bang for the buck and also like safety, relative safety of the optimization, so that we can convince them that it actually is a good idea. So that was surprisingly difficult. I come from like a research background. I worked in research labs before, so this was like my almost first exercise of this kind. That was really not that surprising, but yet it was surprising. So what were the optimizations that we actually chose? Sorry, is there still time? Because I'm sorry. Ooh, all right. Okay, so basically optimizations we only pick 2 optimizations. The second one is almost not worth talking about. It's just sort of standard bytecode level inlining optimization. The other one is a little bit more, it's not complicated, but it's maybe a little bit more unusual. It's like compiler optimization. It basically optimizes I/O in that you try to align the layout of the classes in your application file with the order in which classes are loaded by the VM. If those are mismatched, you'll get cache thrashing, and I/O will just cost you a lot. So Redux has a pass that tries to do that based on profiling. Getting it to work was a different story. We love Facebook. I mean, they produce a lot of quality tools, but if you try to take a tool from one company and try to put it in at work at scale in production, different company, it appears that there's a lot of challenges. We had to fix a bunch of bugs in both the Redux itself and also in the surrounding infrastructure. We upstreamed a lot of those. There were some instructions that were missing. Since I don't really have time, I will not go into details on that. But basically, the automation also took a long time because it involved a lot of moving pieces and a lot of people that helped with that effort. And finally, deployment, right? We wanted to make it such that once it's deployed, there's no further manual effort that's required. But we also wanted to run tests on basically each time the application is pushed to Monorepo, it should be Redux enabled, and it should run all the tests, that sanity and UI tests that we have. And the 2 main components, I will skip the textual description because I have a system architecture slide that will also describe that. I'm probably like super sort of running out of time right now. But basically, we have another piece of CI infrastructure that talks to our device lab. Device lab runs a special device with a special ROM that runs the profiles. Basically, it gives you a list of classes. It gives you a list of classes that tell you the order in which the class have been loaded by the VM, so that you can use it in the build system to rewrite your application file to match that order. That's basically it. That's all that happens. There's another piece that's needed for inlining. Inlining, if you inline at the bytecode level, the stacks that will come from the field will be garbled because you lose information about methods that are being inlined at the bytecode level, and those will have to be recovered. There have been support for this in Redux, but it was kind of broken. We had to fix it. We had to rewrite the remapper and gather data from the when we gather data from the field, that goes to the remapper, and everything is fine. But again, it took a lot of effort. But the good thing is that this all runs sort of without any human supervision at this point. The only supervision is that I get emails if the CI infrastructure fails or something, that happens very rarely. But other than that, it's just fully automated. This is the times, the performance. Basically, we get this. Yeah, this compares 2 different versions of application, basically at their respective windows at a certain time after release. The graph is normalized with respect to the last one that had no optimization, and compares to the first one that actually had optimization. The x-axis shows you this is the 5th, 6th, and blah, blah, 10th day after the 100% rollout of this particular application to the Google Play Store. So that had time to sort of gain enough users for the sample to be actually reliable. So we get about 14, 15% speed up for our writer app. We have about sort of similar to about 15% speed up for the driver app. And inlining is a little less successful. It's about maybe 4.2% speed up. And don't ask me about that dip. I have no idea. We didn't have any outages. But remember, these are 2 different windows for 2 different versions of the app. So it could be anything, like fluctuations in network traffic or overloading of our service. But I couldn't figure out what it was. But this is data from production, though. So it's not like I run experiments and sort of mess something up. Conclusions, we work on a variety of things. The automation efforts I mentioned are not the only ones. There's a bunch more that's sort of in the pipeline. What I wanted to leave you with is that it is challenging to actually do these things in production and at scale, even using tools that already have proven themselves in a similar setting. Sorry for running a little bit late. Last slide is for questions and obligatory legal thing, so that our lawyers are not going to shoot me after the conference. Thank you very much. Thank you for coming. Thank you for staying. And if you have any questions, there's probably no time. Thank you.